Now that we know what it means to be an eigenvector of a matrix, and some of the ways that these objects are interesting, we turn our attention to finding these eigenvectors for square matrices. Throughout this video, let A be an n by n matrix. We're interested in finding vectors v for which there exists a scalar lambda so that AV is equal to lambda v. So we recall from last time that we can think about scaling by a scalar lambda as multiplication by a diagonal matrix with lambda along the diagonal. Explicitly, we see if we multiply the vector v by lambda multiplied by I, then we see that we get a linear combination lambda times v1 e1 plus lambda v2 e2 plus etc. plus lambda n vn en. And of course, if we add these together, we add along the components and we get lambda v1, lambda v2 down to lambda vn. So this allows us to rewrite our original equation, which was a matrix times a vector equals a scalar times a vector, as an equation of two matrix multiplications, a matrix times a vector on the left and a matrix times a vector on the right. So now we can subtract lambda I times v from both sides of our equation. This of course leaves us with the 0 vector on the right hand side. Now the reason why we've done this is we have two matrices multiplying the same vector on the left. This allows us to pull that vector v out as a multiplication on the right of the difference of A and lambda I. When we take the difference of these two matrices, this of course gives us a matrix of the same dimension. So this is also an n by n matrix. Now recognizing that A minus lambda I is an n by n matrix allows us to think about the eigenvectors of our matrix A as solutions to a homogeneous equation. And of course, we've developed lots of tools for solving homogeneous equations involving square matrices. The first is that there are non-trivial solutions to such a homogeneous equation if and only if the matrix B is not invertible. And two, we know that B is not invertible if and only if the determinant of B is equal to 0. So if B is the square matrix A minus lambda I, then this gives us a way to think about detecting the eigenvectors of A. Rather than searching directly for the eigenvectors, we can identify the eigenvalues, lambda, by finding solutions to the equation, the determinant of A minus lambda I is equal to 0. So as you may have guessed, this equation is going to play a major role in our discussion on eigenvalues and eigenvectors. So we give it a name. We call the equation the determinant of A minus lambda I is equal to 0, the characteristic equation of A. Let's do an example. We're going to take a 2 by 2 matrix whose columns are 1, 2, and 2, 1. So to find the characteristic equation for this matrix A, we will first take the matrix A and subtract from it the matrix lambda I. So we're left with 1 minus lambda 2, 2, and 1 minus lambda. Next, if we want to find the characteristic equation, we simply take the determinant of this matrix. And so we see here that the determinant of A minus lambda I is the degree 2 polynomial, lambda squared minus 2 lambda minus 3. So the characteristic equation is, of course, a quadratic equation, and we can find the solutions, or the eigenvalues, for A simply by factoring. So this tells us our two eigenvalues for the matrix A are lambda equals 3 and lambda equals -1. Now, this was not an accident. The determinant for our 2 by 2 matrix came out as a degree 2 polynomial. It turns out this will always be the case whenever we have a square matrix, and the degree of the polynomial will be the dimension of the space that the matrix operates on. So if A is an n by n matrix, then the determinant of A minus lambda I is a polynomial of degree n, which we call the characteristic polynomial of A. The roots of this polynomial are the eigenvalues of the matrix A. So let's work a slightly larger example. So for our example, we'll take the matrix A with columns 0, 0, 4, 1, 0, minus 17, and 0, 1, 8. The first thing we want to do is compute the characteristic polynomial. So we can simply subtract lambda from each of the entries along the diagonal, and then we want to take the determinant of the resulting matrix. For this particular one, I'm just going to use cofactor expansion using the top row. So for the first, we take negative lambda multiplied by the determinant of negative lambda, negative 17, 1, 8 minus lambda, and the second one is negative 1 multiplied by the determinant of 0, 4, 1, 8 minus lambda, and the third entry here will just be 0. So we can compute each of these two smaller determinants using the normal formula for a 2 by 2 matrix. Now that we have the characteristic polynomial, we get the characteristic equation by setting this equal to 0. And of course, I like to think about my leading term as being positive in this case, so I'm just going to multiply both sides by -1. Now, from a basic algebra course, we know that any integer solutions to such a polynomial must be divisors of the constant coefficient. So there are 6 potential values that could be a solution. So we can check each one of these 6 divisors of -4. When we plug in 1, we'll get 1 minus 18 plus 17 minus 4 is 6. And if we plug in -1, we'll get -30. If we plug in 2, we'll get 6. And if we plug in -2, we'll get -78. If we plug in 4, then we see we get 64 minus 128 plus 68 minus 4 is, in fact, 0. So this tells us that lambda equals 4 is a solution to the characteristic equation. That is, it is an eigenvalue. So to get the other 2 eigenvalues, we remember that lambda equals 4 is a solution to the characteristic equation if and only if lambda minus 4 divides the characteristic polynomial. So to see how lambda minus 4 divides the characteristic polynomial, we carry out polynomial long division. First, we will multiply by lambda squared. So when we subtract lambda squared times lambda minus 4, that's the same as subtracting lambda cubed and adding 4 lambda squared. The lambda cubes, of course, cancel out, so we're left with -4 lambda squared plus 17 lambda minus 4. Next, we'll multiply by -4 lambda. So of course, when we subtract that value, we are adding 4 lambda squared and subtracting 16 lambda. That leaves us with 0 for lambda squareds, 1 lambda, and a -4. Of course, this is the same thing as lambda minus 4, so we'll multiply by 1 and subtract the result. So this tells us that we can factor the characteristic polynomial as lambda minus 4 multiplied by lambda squared minus 4 lambda plus 1. So to get the other eigenvalues for our matrix A, we just need to use the quadratic formula. The discriminant of this quadratic is negative 4 squared minus 4 times 1 times 1. That's going to give us 16 minus 4 is 12. Since this is positive, we'll see that this quadratic has two solutions. So we compute the square root of the discriminant is 2 root 3. So our solutions are given by the quadratic formula. Lambda is equal to negative 4 plus or minus the square root of the discriminant, all divided by 2 multiplied by 1. So that gives us 2 plus or minus the square root of 3. So we can see that our matrix A has 3 eigenvalues. Those eigenvalues are 4, 2 plus the square root of 3, and 2 minus the square root of 3. So now that we've seen a couple of examples about how to compute the eigenvalues for a matrix, up next, we're going to talk about how to use these eigenvalues to find the eigenvectors.